the size of a hadron, which is of the order of a Fermi, just from the uncertainty principle, you're going to have, this particle's going to have a momentum. Remember, h bar is equal to 1. So the uncertainty, the momentum, 1 over delta x. Delta x is about a Fermi, and we've just seen a Fermi is about, if we're looking in the previous view graph, a Fermi is about 5 GeV to the minus 1. So we've got a fifth of a GeV for the momentum. That's typically what we'd expect. Now that momentum is giving you an energy which is giving you a mass. So this is a constituent mass of these quarks inside, say, a proton. Now a proton's got 3 quarks inside, and if we give those quarks a mass of something like 330, we can reproduce the masses of the known hadrons. If you go up to a strange hadron, such as a lambda, which is made of a U, D, and an S, you see that the S is a bit heavier. And then if you look at charm particles, which are mass about 3 GeV, you can see the mass of the charm quark's going to be about 1500. So these are just what we call the constituent masses, the non-perturbative constituent masses. Now let's look at the other side. Now if you hit a hadron very, very hard, so we're going to hit a hadron very, very hard. When you hit the hadron, to start with, it acts as if it was totally free. We'll see how that comes about. So it never gets out of the hadron, but the action of this probe that you're hitting it, say you're hitting it with a very, very energetic photon, the behavior of that system acts as if when it's hit, this thing was free. And so that would be the real mass that you should be associating with that quark. But of course it's technically very difficult to do that for light quarks, because they never get outside of this hadron. So we've got to explain that in a bit more detail. But we can determine that mass by indirect methods, and these are the masses that you'd get there. It's these light masses that are very different from the constituent masses. When you get heavier and heavier, these two numbers get more similar. And so these are the masses that will occur in the QCD Lagrangian. Now what about forces? Let's look quickly at the forces. Let's start with the weakest of all forces, the gravitational interaction, and let's start with Newton's non-relativistic theory. And we have two masses separated by a distance r, then the potential between them is just the Newton gravitational constant, the product of the masses, over the distance between them. That's just Newton's non-relativistic theory. Now, we are interested in protons. So let's make these two particles protons, and let's have them one natural unit apart. Now, a natural unit is going to be formed from h bar c and a mass. So what is a natural unit of length? Well, you can see if you put an angular momentum on the top and a momentum on the bottom, you're going to get something of the dimensions of a mass, of a length. So that is going to be h bar over mpc. From our units, that's the natural unit of length. So if we're wanting to get a dimensionless measure of the strength of this interaction, we have to consider the potential energy of two protons a unit distance apart over the rest mass energy. That would give us some idea of the strength of this gravitational interaction. So here we go. We will put Gn here, the product of the masses, mp squared over r. R is just h bar over mc. So we've got, and then we've got to take the rest mass energy, the mass of the proton, times c squared. This reduces to just Newton's gravitational constant, m squared over h bar c. H bar c in our units is just 1, so this means we've got g mp squared. And that turns out to be, when we look at the Newton's gravitational constant, this product turns out, it's dimensionless, turns out to be 10 to the minus 40. That's a tremendously weak interaction. And we can essentially ignore this in laboratory particle physics. There's no possibility of this affecting the results. So why is that the force that we see? The only force we see, it's that keeps us on the ground. Such a weak force, and it's weak because it always comes in with the same sign. It's always positive, so all the masses in the Earth are attracting us to the Earth, whereas the other forces, like charge and everything, are just going to be positive and negative and balance out. So this is really the first curiosity. The force that we see in our lives are dominated by it, that we can actually do experiments from, is totally irrelevant for laboratory particle physics. Now that was Newton's theory. But if we went to general relativity, it just doesn't couple to mass, but it couples to total energy. So our relationship before, that we had g m squared is order of 1, is really g e squared the order of 1. Now you can see that this strength is going to be the order of 1 at an energy, the square 1 over the square root of the Newton's gravitational constant, which if we work it out, comes out to be 10 to the 19 GeV. So if we are dealing with systems with energy 10 to the 19 GeV, which are far outside of anything that we can do on this Earth, then we cannot neglect gravity. This is the Planck energy, and at that stage, it's going to be relevant. It's going to be the same. It's going to be the order of the other forces. So that's interesting. What about quantum field theory? We're going to exchange a graviton between the masses. It's an infinite range, so we'd expect the graviton to be zero mass. The coupling is a measure of the probability of this thing being exchanged. So, and we've seen that's very, very small, so it's going to be very, very difficult to detect in experiments, to detect gravitons. In quantum field theory, this fluctuation of the graviton being exchanged is really a fluctuation of the metric tensor of space-time, g mu nu. And that's why this, because we've got two Lorentz indices, this is why this graviton has got spin 2 nature. Unfortunately, gravity doesn't yield a finite or renormalizable theory. There is huge problems to get gravity into the fold, and an awful lot of current research is trying to get gravity compatible with quantum field theory. Okay, so that's a sort of overview of gravity. Let's go on to the electromagnetic interaction, the next one. Again, we start with the basic law like Newton's law. In this case, it's the product of the charges and inversely proportional to the distance. And we've got this 4 pi epsilon naught on the bottom. So we've seen that charges are of the order of the electron charge or the proton charge. So let's take two proton charges a unit distance apart. And a unit distance, remember, is h bar over mc. We're just doing the same as we did before. And we're wanting to get a dimensionless measure, like we had for gravity, where we had 10 to the minus 40. What do we get for the electromagnetic interaction? The dimensionless measure is an electrostatic energy 1 unit apart from these two charges over the rest mass energy. In this case, the dimensionless measure is called alpha, the fine structure constant. Okay, the electrostatic energy is just the product of the charges, 4 pi epsilon naught on the bottom, and the 1 over r, which is h bar over mc squared. In this case, notice m cancels out, and one of the c's cancel out, so we've got e squared h bar c over 4 pi epsilon naught. Now epsilon naught, we are in the vacuum here, is equal to 1, so we've got e squared over 4 pi. Remember that our units are h bar c equals to 1, and this thing is equal to 1 over 137, independent of the mass. The smallness of this thing means quantum mechanics, non-relativistic quantum mechanics, was adequate for the hydrogen atom, and that's why quantum mechanics actually was first found in this situation, talking about the hydrogen atom. So that was a bit of luck, really. Particle physics uses rationalized Gaussian units, called Heaviside Lorentz units. We've got epsilon naught equal to 1, and the 4 pi's occur in the force equation and not in Maxwell's equation. So that's what's generally used in for electromagnetic processes in particle physics. So in quantum field theory, what happens here? We just exchange the photon. Whereas we're exchanging the graviton before. Again, it's got infinite range, so this particle, if it's going to get, you're going to pay a price because it's off its mass shell. It's off its mass shell. It's got to go an infinite. It can go only an infinite distance if it's massless. And the photon is going to be described by an electromagnetic potential, which only has one Lorentz index, so it's going to have spin 1. So it's a rank 1 tensor, spin 1. Quantum electrodynamics can be, it's equivalent to a U1 gauge quantum field theory. And clearly we'll have to explain this better. The coupling turns out to run. So as you probe a charge closer and get closer and closer to the charge, the vacuum polarizes into E plus E minus pairs, and as you get closer to the charge, you get less and less screening from these vacuum E plus E minus pairs, and so the charge increases. So you can see the fine structure constant is really a misnomer. This, called the fine structure constant, it is neither constant nor is it fine. It just describes the gross properties of the hydrogen atom, not the fine structure. So it's a double misnomer to call that the fine structure constant, but that's what's done. Now what about the strong interaction? Now the strong interaction in the 1960s, we go back to the 1960s, and we've got a nucleon and a nucleon, so a proton and a proton. And the idea is, well, we know that the lightest hadron is a pion, so they're exchanging a pion, and it turns out that the coupling here is about 15. The E squared over 4 pi was 1 over 137. Here, G squared over 4 pi is the order of 15. Now, quantum field theory is based, the results of quantum field theory are based on doing a perturbation expansion, so you keep the lowest order diagrams, and if you've got every time a vertex, and you've got some coupling that's sort of 1 over 100, you can have a very convergent perturbation theories, because you clearly can exchange everything you like here, but here you've got no chance of a quantum field theory. And in those days, the only quantum field theory we had was QED, and that was thought to be anomalous. In those days, it's thought that this would emerge from using sophisticated kinematics, in other words, analyticity, crossing, and unitarity on the probability amplitudes or the S matrix. And you would get a consistent set of amplitudes for these 3 different regions, and they would tell you from the analyticity what particles you had. I don't know whether I should attempt to explain that more. Perhaps I should. So let's take pi-pi scattering. Let's try another pen. So we take pi-pi scattering, and we take pi plus, pi minus. No, nothing seems to be working here. Let's try this one. Ah, that's much better. So we take pi plus, pi minus to pi plus, pi minus. Now, crossing means you exchange 2 particles. Say you exchange these 2 particles. Then again, you would see if you took this over the other side, you'd get, well, in this case, you'd get pi minus. This would, oh, sorry, that would, If I took this over this side, this would have become pi plus, pi minus, goes to pi plus, pi minus. If I cross this one with this would become here an ingoing pi plus, so I'd have pi plus, going to pi plus, pi plus. And it happens that the kinematic regions for these three are non-overlapping. So that's the crossing. So I've used crossing to relate these three processes. Actually, two of them are the same. Now, if we use analyticity, you could imagine the amplitude over this thing, this region here. This is sort of in two dynamic variables. You're going to get the energy of this process is going out here, and you've got pi plus, pi minus. Actually, it forms a resonance here. So we've got a pole sticking out of this sheet that's overlying here. This is the row resonance. And you've got another row resonance in this one, because this is the energy going up here. This hasn't got a resonance. And it was hoped that by looking at the analytic properties of this sheet, only the allowed particles would emerge. So they would, it's called a bootstrap. They would pull themselves from their bootstraps. This idea failed completely. But that's what was happening. So the only self-consistent solution that satisfied this was thought to give you the particles, like the row resonance is bootstrapped that way. It's an interesting idea, but it completely failed. From the mid-60s onwards, it's interesting that hadron spectroscopy, such that you group particles together with like properties. These have all got spin a half. And these have got spin 0. You group them together in multiplets, and it turns out that those multiplets are such that they're made up for the baryons of 3 quarks and the mesons of a quark and an antiquark. This is indicating that you've got building blocks of hadrons coming in 3 colors necessary for fermion statistics. You can't have identical particles being interchanged here, so we just ad hocly say they've got color. So this is the first time we've met color. And surprisingly, deep inelastic scattering confirmed the existence of these things. You hit it and it seems to emerge. It doesn't emerge, a jet of particles emerge instead. But the proton you're hitting acts like a current bun with 3 currents in it, and it acts free to start with and then gets confined, and you produce a jet of particles. So you actually see these things. So QCD was based on this, taking this much more seriously, this color, a color gauge field theory, and it solved the dilemma, as we will see. And we've got gluons being exchanged in this situation, the carriers of this gauge field theory. And they've got to be massless, again, because all gauge, we've got to satisfy gauge invariance, and this requires you to have massless gauge bosons. Interesting, the coupling runs in the opposite way to the QED coupling. Okay, let's go on to the weak interaction. That started by the beta decay of nuclei. That was the hot topic in the 20s and 30s of particle physics. And you've got 4 fermions interacting together, neutron changing into a proton inside a nucleus changing into a neutron, and another one is muon decay. Well, originally, Fermi thought that this was conveyed by a point interaction with the 4 fermions interacting at a point, and you can interchange an initial to a final state as we've done over there. If you can have an ingoing, you can take this over this side, so you can have an ingoing E plus on a neutron would make a proton and an antineutrino. The coupling turned out to be quite weak, 10 to the minus 5 for this situation. So the Fermi coupling again has got dimensions of inverse energy, but it's got, this product is weak. But it turns out that local lowest order field theory, where you just calculate the lowest order point-like diagram, is okay. It does well for all these processes, but of course the theory is not renormalizable. So you don't really have a quantum field theory, you just have the lowest order field theory. We now know Fermi's idea was pretty good. This is pretty good. There's sort of three things that are wrong with it. First of all, to make this field theory work, you've got to exchange a particle. Turns out to be a massive W boson. That vertex then is not a point-like vertex. It's almost a point-like thing because this is very, very heavy. And this W couples universally to all these pairs of these things here. It's got charge, so these must be one unit of charge different. When I say universally, it's almost universally. There's some kind of rotation going on here. So there's a rotation in quark space, and it turns out now we've got a rotation in lepton space, CKM mixing, or MNS mixing, or PMNS mixing, depending on the notation you're using. So this W couples to all these doublets universally. Here's a doublet. It's this doublet we're looking at with a coupling G. This thing here, again, coupling to this thing with the same coupling. So that's decided improvement. That means that we can start thinking about a quantum field theory. So what we have done is, instead of having a point interaction, I've had almost a point interaction. But these are very massive, and it looks like a point interaction. So perhaps we can, as we're dealing with doublets, perhaps we can have an SU2 gauge invariant thing with 3 W's going across here. Again, they're going to be spin 1. They're going to be spin 1 feels they've got a Lorentz index. Well, let's just see what the mass would be, roughly. Let's say that the weak interactions are weak, not because they're intrinsically weak, but because you've got a massive particle going across here. So the general coupling, this green thing, the Fermi coupling constant, is G squared over the mass of that exchange particle. Remember, this has got inverse dimensions of a mass. This is really the propagator of the W going across on the bottom here. So let's say they're the same strength as electromagnetic, but they've got a massive particle going across. Well, what's that mass? Well, that mass is going to be E over root GF. GF is 10 to the 1 over GF is 10 to the 5. The square root of it is 300. So it's 300 times the mass of the proton times the electromagnetic coupling, which we've seen is 4 pi over 137. That turns out to be 100 times the proton mass. So we'd expect this thing here to be about 100 times the proton mass if it was weak because it was a massive particle going across here. This is not quite correct because it would be nice to say G is equal to E, but the weak interactions mix with the electromagnetic interactions, and the mixing is given by this sine theta W. In other words, the neutral particles of both the electric and the weak interactions, the ones that we see, are coming from gauge eigenstates. These are the symmetry states. The SU2 things are W naught, W plus minus, and another U1 generator, B, and they're mixed in that way. So these are the gauge eigenstates. The mixing is given by sine squared theta W. Weak mixing angle, which squared is about 1/4. That's one. So the W is one thing Fermi didn't have. The other thing, which is really puzzling, is that parity is maximally violated in weak interactions. W bosons only couple to left-handed quarks or leptons, or right-handed anti-quarks and anti-leptons. You've actually destroyed symmetry completely, the left-right symmetry. That you couldn't do it more than just having left-handed. For relativistic particles, left-handed is spin direction in opposite the direction of motion. Right-handed is in the direction of motion. You can see that's only true for very high energies or for massless particles, because you can overtake that and change the spin direction. Now, this assertion, which is really staggering, was soon checked. It could have been checked any time, but nobody thought of checking left-right symmetry. But it was checked within 6 months and found that this was actually true. The other puzzling thing is these massive bosons, because the quantum field theory doesn't become renormalizable if you've got massive bosons. And the problem is the longitudinal polarization states, which grow with energy. This was solved by a Higgs mechanism, which ate these longitudinal polarization states. The Higgs was a doublet, complex doublet with 4 free fields. 3 of them were eaten to give the longitudinal polarization state, leaving you with one spinless zero particle, the Higgs. So that's the Higgs mechanism solving this problem. Okay. Let me give out this. So that summarizes our little discussion. We've got to explain this much better, but this is where we are at the moment. So, this is just summarizing what I've said. Let's see if we can pick it up on here. Well, here is the QED part. We're saying QED is a U1 gauge field theory. Here is QED, and the exchange particle is the photon. That Q there is the generator. We'll see what a generator means. It's the charge generator. It acts on the charge. So that's the QED part. What did we do next? We did the strong interaction next, and we found that we're going to have an SU3 gauge theory and with the gluons being exchanged. So that C, you see these subscripts all depend on different things. This is not a generator, this is just the word color on this one. So that's quantum chromodynamics. Now we've got the weak interactions to worry about. In the weak interactions, you can see that we are starting to talk about SU2 because of these doublets and these 3 gauge bosons going across. So it would have been nice to feel that we were talking about that part of it. And we've got a triplet of W bosons, 2 charged and 1 neutral. And the L this time stands for the fact that they only couple to left-handed states. But then we saw it was even worse than this. They were mixed. So these 2 interactions were mixed. And so you've got 4 gauge bosons here, which are these 4. So we have to have another U1, which has got a particle B, a gauge eigenstate B. And the 2 neutral members, that's neutral, these 2 form some linear combination of these 2. And here are the linear combinations. These are the physical states we see in experiments. These are the gauge eigenstates that are fundamental to this SU2L cross U1Y. Now that's hypercharged. It's not the same thing as charge. This gets broken to QED. This is a sacrosanct interaction. It's only at some just around about the W energy and above that this symmetry becomes correct. So we've got electroweak symmetry breaking here, down here. We're saying in the standard model it could be carried by the Higgs boson. But you could have the Higgs mechanism without having a Higgs boson, so that we don't know. We are right here now. We're sitting on top of going to find the answer to this, because the LHC is going to start and we're going to probe the electroweak symmetry breaking. So this is where we are. And you can see it's messy. This is sort of messy. This is nice and clean at this stage. This was clean. But the weak interactions are mixed in. It's not pretty at all. But they all have the same kind of structure. They all have this, we must have a picture of this, well, not that one. They all have this structure. So it's suggestive that at some energy, all these couplings go together, and we've got some grand unified theory that combines these groups together. and we could count the minimum group it could be as SU5. But when do the couplings come together? Remember, the weak interactions is, what did we say, 10 to the minus 5. This was much stronger. You have to go up to 10 to the 16 GeV for that to work. We have no idea what the group is. It could be SU5, SO10, or anything there. And then we've got gravity. We talked about gravity, and at 10 to the 19, that gets the same strength as this lot. Can we unify that somehow with a spin 2 particle? These are all spin 1s. So that gives us a view, a very, very worm's eye view of what I've been talking about. We are, in the standard model, believing that there's a Higgs particle. That would be, the standard model is in blue. The red stuff is beyond the standard model. And you can see that we are a long, long way from this area here. We will have to infer that, not directly, but indirectly, if we're going to learn anything about that. And we will discuss this a bit. Okay. Have I run out of sheets here? Are we still on the sheets? You want more yet? You need another sheet. Or you should have told me if please, somebody do tell me. I don't know if there's enough there. Has everybody got the sheet of the previous one? Have I got enough sheets? Okay. Are there any questions? For some of you, what I've said you will be very familiar with so far. And for some of you, it might be a little bit new. What I'm hoping very much is for those that are experts at this will help the people that are not experts at this. So I'll try and sort of indicate what are the experts. Those people that have done Cambridge Part 3 will certainly be experts. Those people that haven't done a course in, haven't done the Dirac equation. How many people here haven't done the Dirac equation? Yeah, at least 5, yes. So those people, how many people here have done quantum field theory before they came here? Now, so there's another 5 people, or 6, 7, should get together with the people that haven't done the Dirac equation and help them. Is that all right? That's my hope. Okay. Right. We're changing topic a bit. This is still the overview. What do we measure? We measure cross-sections. We measure the area of an interaction in terms of barns. Barns are the unit we use, which is 10 to the minus 28, which is ridiculously large. It comes from the nuclear physics thing. Our cross-sections are never going to be barns, but we still use the unit barn. We've seen that h bar c, we looked at those units and we saw h bar c was about 1/5 the GeV Fermi. So if we square this thing, h bar c is still going to be equal to 1, GeV squared, Fermi squared. We're going to try to get something with the units of length. And you see a Fermi squared is 10 to the minus 15 of a meter squared, 10 to the minus 30 of a meter. A millibarn, which is a thousandth of that, is 10 to the minus 31 a meter squared. So these two things are correct to within a factor of 10. So we've got to multiply this by 10, and you can see that now we've got a millibarn is 1 over 0.4, which is 2.5 GeV to the minus 2. So our previous thing relating Fermis to GeV, now we've related millibarns to GeV to the minus 2. Now experiments nowadays are done with circular colliders. Counter-rotating beams hitting head-on. The crucial thing in a collider is its luminosity. What is its luminosity? Its luminosity is essentially how many times the beams go through each other in the collision mode. So each beam contains k particles per bunch. There are n bunches going round in a ring, and the frequency that they pass round the ring is f, and the cross-sectional area of these beams I'm calling A. The luminosity is the number of particles essentially passing through each other, which is the product of these things over the area. And if we look at the units, this has got to be an area on the bottom and a frequency here which is seconds to the -1, and these are just numbers. Having got this luminosity, you can then take the process you're interested in, whatever cross-section it has, sigma, multiply by this luminosity, and say how long you're going to do the experiment, capital T, and that's going to give you the number of particles, the number of events you're going to get of the things that interest you. As an exercise, go to LEP 1. Well, we should mention what LEP 1 is. Am I going forward? I'm going the wrong way. Right. Onto here. I won't bother to remove this thing at the moment. Here is LEP, which ran at CERN from 1981 to 2000. The E plus E minus collider, which was a Z factory, sitting on top of the Z. Z had a mass of 90, and that's where it sat. Unfortunately, it didn't reveal any new physics. It just told us the standard model was even better than we thought. And we got a lot of precision, but no conceptual new thing. So they, LEP 2, they went to the limit that they could to try and find the Higgs boson. And though they got kind of little bits of hints, they didn't find the Higgs boson. And the luminosity of LEP 1 was 20 10 to the 30. So here it is, 2 times 10 to the 31. And the cross-section, I give you the cross-section for how many, for producing a Z, which is 40 nanobarns. And I ask you how many of those Zs will decay into mu plus mu minus per second at LEP 1. That's a very relevant thing if you're an experimentalist. You can see the luminosity coming in here. We're now at the LHC, which is down here. It's meant to start in this November, meant to start long before that. And it's going to have ultimately an energy of 7 TeV in both beams. So the total energy is going to be 14 TeV, or 14,000 GeV. It's the energy. The luminosity, the design luminosity, is 10 to the 33, going up to 10 to the 34. So I put in 10 to the 33 here, and I'm asking you how many Zs you're going to get from a cross-section here at the LHC. That's an interesting number to calculate. You have to look up the particle data tables to see the branching ratio for this thing, so I'll leave that for you to do. But please do that problem. Now we come to the colliders here, and we've mentioned these two. I'm using the wrong thing, I can see that. Then we had an electron-proton collider. You remember that machine? Remember we said we took a proton and we hit it very hard with a photon. That's obviously an interesting thing to do because you're looking at the structure of the proton and you're seeing the quark content of the proton. This is a pretty energetic machine. It's got 300 JeV. The Tevatron, which is a proton-antiproton hadron collider, which is still running and could well find the Higgs, because it's got enough energy to find a light Higgs. Been running for nearly 30 years, and the luminosity is about 170. So that could find the Higgs ahead of CERN. It hasn't really got enough luminosity or enough energy. The energy and the luminosity are the vital things. Why do we use colliders rather than fixed target machines? That's something should be exercise number 2. Why do we use circular colliders where beams pass through each other rather than hit a massive target? Why do we? Tell me. Yes. You get much more center of mass energy if you hit head-on than if you hit a stationary target. You can see that because if you hit a stationary target, a lot of energy, instead of going into the mass, is going into the momentum of the thing you hit. But it's even worse, because if you work out from relativity, you see one grows as energy, the other grows as the root of energy. But work it out and just check that that's true. You see, unfortunately, if you want to turn a beam round, you're going to radiate something to turn it round. Something has to go off in this direction to conserve momentum, as it were. So if you're going to turn something round, you're going to lose a lot. You're going to have a power station to keep this going. And the tighter you make that ring, the more expensive it'll be, because the more energy is going to be sent off. But on the other hand, if you make the ring too big, you'll have to pay for a huge number of magnets. So there's a compromise here. So you can see, from experimental point of view, this is an interesting balancing equation. Well, we've discussed these machines here. There are also lower energy machines for looking at those quarks, which are the energy of about 5 GeV, and also looking at something 5, which is about 1 GeV. They're looking for detailed properties in the standard model. Maybe we'll see beyond the standard model physics by having standard model precision measurements that don't quite match the standard model predictions. Will indicate beyond the standard model physics from some exchanges that we haven't got in the standard model. Here we are. Here's the LHC. That's the luminosity. Now, with that luminosity, if we put a cross-section of 1 nanobarn, which is 10 to the minus 9 barns, turns out to be 10 to the minus 33 centimeters squared. So if we measure the cross-section here in nanobarns, this is just the number of events. It's the same as the number of events. So let's plot various things. The total cross-section, the number of events per second, is 100 million events per second interacting in the LHC. If we're interested in separate things, this is the Tevatron and this is the LHC. This is the energy going up there. Here's the LHC here. If we're interested in particular things producing BB bar pairs, see there are 1 million a second. 1 million BB bar pairs produced a second. That is better than any B factory here. This is E plus E minus focusing on that mass to produce BB bar pairs, or twice the mass of the B quark. They're going to be obsolete as soon as the LHC gets this thing together, because the number of events are much, much bigger, so we can investigate flavor problems and CP violation. Here's the W and the Z. Here's the thing I asked you to calculate. Here you're producing 2 per second or 20 a second in these decay modes. Maybe they can be used for the luminosity, how strong, how many interactions you actually get, as well as precision measurements of the W and its width. Top quarks, this thing that's 170 times the mass of the proton, you're producing 1 a second of these pairs down here. These are the things we're interested in. Supersymmetric particles, or the Higgs. They're coming in at few a minute. That sounds a lot. But we are getting 100 million events a second. We've got to go down all these orders of magnitude. This is a really formidable experimental challenge. We've got to get under this standard model background and see these things down here. Orders of magnitude under what is coming from the standard model, which we know will come. Now you can see the experimental problem, and now you can see the tremendous achievement of these experimentalists feeling confident that they can unearth something down here. You see this machine, there's another machine in here, CERN PP bar collider, that discovered the W and the Z. To discover the W and the Z somewhere down here, they had to go down 6 orders of magnitude or so to discover this. We've got to double that, maybe not double it, but we've got to go down 10 orders of magnitude to start probing that. It's even worse than that, because the Higgs, that's production of it. The Higgs has got to decay into something we can see. So though we're going to be probing that sector, it's going to be a tough job. Now, symmetries have been obviously underlying everything. And this is too late to talk about symmetries. So Are there any questions? Just obviously a very quick question. You don't want to let me start talking. Is this okay? This is a kind of reasonable rate. Okay, is it? Not too slow.
Do you follow any textbooks?
Not really, no. No, I mean, there are a whole set of, there's a reading list. Things move along such a rate that, you know, that yes. But, yeah, yes. Okay, so we'll go again tomorrow. But do tell me when I run out of notes, because it's, perhaps you would be the most responsible person to tell me when we're off notes. Okay then, thank you very much. Oh, sorry, you got a question. Any more sheets? Is there any spare sheets over here? Is there any other spare sheets? Are they all finishing up over here? Thank you. Thank you. Which one is it the want?
Yeah, that one. Also, is that a
Fun?
list we didn't sign?
You didn't sign that. Has everybody signed this? Because I want to... There's a sheet so I get your name. So I'll go through your names tomorrow so I know who you are and what you're doing. Has everybody signed this sheet? Apart from the back row here. Okay, thank you. That's the one, is it? You haven't got one either. Right. So everybody's got sheets they want. Very good.